Hello everyone, I welcome you all to the course UAV Design, and in today's lecture we're going to see about the aerodynamics of fixed wing, quadcopter and hybrid unmanned aerial vehicles. Basically, the aerodynamics of unmanned aerial vehicles are fundamentally determined by their configuration, which dictates how they generate lift, maintain stability and transition between flight regimes. The three primary configurations of unmanned aerial vehicles are fixed wing, quadcopter and hybrid unmanned aerial vehicle, which operate under distinct aerodynamic principles. The first part, fixed wing aerodynamics. The fixed wing unmanned aerial vehicles majorly rely on the forward motion of the vehicle to generate a pressure difference across the wing surfaces, which creates the lift. Lift and drag generation. Lift is generated perpendicular to the flight path and is a function of air density, velocity, wing area, lift coefficient. The lift equation, the lift force equation is L equals to half rho v square S CL, where rho is density, v is velocity, S is wing area and CL is coefficient of lift. Drag is an aerodynamic force which opposes motion, and it consists of, or we can say it is a combination of foam drag and skin friction drag, termed as parasite drag. And this drag opposes the motion. Along with this parasite drag, it will have even lift induced drag. It is a drag which is formed due to the formation of lift or due to the generation of lift. We can write the drag equation in a relationship which is given by drag polar, that is CD equals to CD naught plus KCL square. K is again 1 by pi into EAR. K is 1 by pi into EAR, where E is Oswald's efficiency and AR is aspect ratio. The stability and control of fixed wing aircrafts. The stability is achieved through auxiliary surfaces. The horizontal tail provides longitudinal stability and trim, while the vertical tail ensures directional stability, which is weathercock stability. Control is managed by deflecting surfaces, ailerons for roll, elevators for pitch and rudders for yaw. These are the three primary control surfaces. The performance limits of fixed wing unmanned aerial vehicles. Stall occurs at high alpha, that is high angles of attack, when flow separation on the upper wing surface causes a sudden decrease in lift and increase in drag. These unmanned aerial vehicles generally offer high endurance and range but cannot hover. Hover is a condition where the total weight of the vehicle is being balanced with the lift. Neither it will move in the forward direction or it will move in the rearward direction. It will hover at one particular place. It will maintain a constant altitude and it will hover there. The quadcopter. Quadcopters generate both lift and thrust through four rotating wings, which are called propellers, allowing for vertical takeoff and landing and also hovering. Lift and thrust mechanism. Here lift is the vertical component of the total thrust produced by the four rotors, which is given by L equals to sigma T into cos theta. Thrust is proportional to the square of propeller's rotational speed. Can simply say T is directly proportional to propeller's rotational speed. T is directly proportional to omega square. torque balance and yaw. Quadcopters use two clockwise rotating propellers and two counterclockwise rotating propellers. Here we can see we have clockwise, one diagonal same, and the other diagonal is having counterclockwise. Yaw is controlled by varying the speeds of these pairs to create a torque imbalance about the vertical axis. The drag characteristics of quadcopters. Quadcopters generally have higher drag than fixed wing unmanned aerial vehicles between range of 0.2 to 0.4 because their bodies are not aerodynamically optimized and their engines are exposed. Flight states and safety. Vortex ring state. It's a dangerous condition during rapid vertical descent where the rotor enters its own turbulent recirculating wake, leading to a loss of lift and stability. It's a condition, right, when these rotorcraft, when these quadcopters are moving up vertically or when it is coming down vertically, when it comes down, it creates a lot of wake, and when during that wake, when those propellers interact with that wake, it will create this vortex ring state. The ground effect. Proximity to the ground reduces induced velocity, increasing thrust for a given power setting. This is a schematic of a quadcopter where we can see that part of the thrust which is providing the lift from this part we can see, and this part of the thrust provides the forward motion to the quadcopter, and on the opposite side we have drag force, and towards the ground we have weight acting, which is a weight force. And similarly, in the previous slide we have seen about VRS. So this is the induced flow before vortex ring state, and this is the vortex ring state where when your quad, assume this quad is coming down, right, it is descend down vertically, so it will create some wake, right, it is pushing some force down. So when that force is coming down and parallelly your quadcopter is coming down, it will experience this vortex ring state. This is how it looks like. Hybrid unmanned aerial vehicles or convertible unmanned aerial vehicles aim to combine the hover efficiency of a helicopter with the high speed cruise and endurance of a fixed aircraft, of a fixed wing aircraft. The common configurations for these hybrid unmanned aerial vehicles are: the first one, tilt rotor. Rotors are horizontal for VTOL and tilt 90 degrees forward to act as propellers for cruise. For example, Bell Eagle Eye. We have seen this in our previous lectures also. Then the second configuration is tilt wing. The entire wing or the entire motor assembly tilts from vertical to horizontal. This is the another configuration. Tail sitter is the third configuration in this hybrid unmanned aerial vehicles, where the entire aircraft body sits on its tail for vertical takeoff landing and pitches forward for level flight. Example, Martin UAV VBAT. Then comes quad plane. It features a dedicated quad rotor system for lift and a separate propeller for forward thrust. It will be like this, a quad plane. It will have propellers, a quad like this, quad will be there, and it will also have a propeller at here so that it can also function like a fixed wing unmanned aerial vehicles during cruise. Takeoff will be vertical, and cruise will be horizontal. So once it attain the altitude, it will move further in forward direction. The transition aerodynamics. The transition phase is the most complex. Designers must manage wing stall, that is transition down, by using high lift devices like flaps to maintain attached airflow as the forward speed decreases and the wing angle of attack effectively increases. The trade-offs for this hybrid unmanned aerial vehicles are: hybrids often suffer from a payload weight penalty because they must carry structural components for both flight regimes, that is for vertical takeoff or landing and horizontal cruise. A major issue is that the fixed pitch propellers used in many hybrids are not optimized for both high torque hover and high speed cruise conditions. This is a hybrid unmanned aerial vehicle flight path. So it will have a VTOL mode, takes off. After attaining an altitude, it slowly moves in forward direction, and during this change from here to here, there is a transition, and then it moves in the forward flight, and again at the time of landing, first it will change from this forward flight to vertical takeoff mode. It will transition, and then it will descend down in VTOL mode, vertical descent mode. Here it is landing. This is takeoff. In the both cases, this is vertical takeoff and this is vertical landing. Only the cruise is horizontal, level cruise. The aerodynamic comparison summary of fixed wing, quadcopter and hybrid unmanned aerial vehicles. The primary lift source for fixed wing aircrafts are wing. For quadcopters, it is rotor, and for hybrid unmanned aerial vehicles, wing during cruise and rotors during hover, vertical takeoff, vertical landing. Hover capability for fixed wing unmanned aerial vehicle is no. Quadcopter can hover. Hybrid unmanned aerial vehicles can also hover. Endurance and range of fixed wing unmanned aerial vehicles is high. Quadcopter will have less endurance and range when compared to fixed wing unmanned aerial vehicles, and hybrid unmanned aerial vehicles will be having moderately upper hand in this endurance and range. Gust sensitivity, it will be very high for low wing loading in fixed wing unmanned aerial vehicle class, and for quadcopters it will be very low because of high blade loading, and for hybrid unmanned aerial vehicles it will be low for hover and it will be high for cruise condition. Hover efficiency for fixed wing unmanned aerial vehicle is very low, quadcopter is very high, and hybrid unmanned aerial vehicle is moderate. Conclusion: fixed wing unmanned aerial vehicles, it generates lift using forward motion over wings where airflow creates the pressure difference. So we can see air over here which is passing over the fixed wing, and this air, when it is moving over the wing's upper surface and down surface, it is creating a pressure difference. The bottom surface will be having high pressure and the upper surface is having low pressure, and due to which it will generate lift. Because of the pressure imbalance, there is a lift generation because this is having high pressure. So it will push the vehicle upside, it will be lifting it. Lift depends on air density, velocity, wing area and lift coefficient. Or we can say lift is a function of air density, velocity, wing area and lift coefficient. Drag includes parasite drag plus induced drag, and it obeys drag polar relation. Here in this parasite drag, it is, we already see that we have seen it is a combination of two drags and plus induced drag. It is controlled by surfaces such as ailerons for rolling, elevator for pitch, and yawing we use rudder. Pros: high endurance, long range and efficient. Cons: cannot hover, stall occurs at high angles of attack. This is the flow over an airfoil which shows the perpendicular force, aerodynamic force is lift, and parallel to the relative wind is drag in the opposite direction of the flight regime. This is the chord line, and the angle between this axis and this chord line is high angle of attack. Using rotating propellers, quadcopters use rotating propellers to generate both lift and thrust. Lift equals the sum of thrust from all rotors. Yaw control is via torque imbalance, that is clockwise rotating propellers and counterclockwise rotating propellers. Higher drag due to exposed structures. So we can see from here the flow over and quadcopter. This is giving the propeller thrust, right? Both are giving the propeller thrust. We are taking just an example of a propeller, not a flow over quadcopter. This is a quadcopter's propeller, right? So it will have a propeller thrust in vertical direction, then component of thrust providing lift, component of thrust providing forward motion. That is because of the balancing, counterbalancing of CW and CCW. This is the weight which is acting towards ground, and this is the drag which is in opposite direction, because your quad is moving in this direction, hence the drag is in this direction. The flight characteristics: it can hover and perform VTOL, and it is vulnerable to vortex ring state during descent. It benefits from ground effect near surfaces. Pros are excellent control, hovering capability. The cons are low endurance and range. This is the quadcopter. The control of a quadcopter, we can see we have here propellers 1, 2, 3, 4, right? And in forward view, we can see that thrust will act in upward direction and drag will be acting in downward direction. This drag is nothing but weight in this case, right? So in order to roll right, it will move here. It will increase the right. So it will move, roll right, roll left, pitch forward, pitch backward. So all these forces we're gonna see in the next lecture. But as of now, let's see. It has thrust here, and then the weight which is down because of this force which is going up, that is termed as drag, but generally it is weight. Roll left, roll right, pitch forward, pitch backward. These are the controls and the movements of quadcopter. The hybrid unmanned aerial vehicle, it combines rotor based lift for hovering and wing based lift for cruise. The types are tilt rotor, tilt wing, tail seater and quad plane. Transition phase, hover to forward flight, is aerodynamically complex. It requires careful stall management using flaps and control strategies. Its trade-offs: heavier due to dual systems, propellers often not optimal for both hover and cruise. Advantage: it's versatile, it can hover, it can have long range flight, but disadvantage: its design is very complex and efficiency compromises here. So You can see that we have rotors here, 1, 2, 3, 4. There are 4 rotors which will help this unmanned aerial vehicle to lift off vertically and even land vertically, vertical descent, and then during cruise it can move in forward direction. This is the hybrid unmanned aerial vehicle flight transition. So it goes up, then it transits, vertical tail, right? This is tilt wing concept. Then again tilt wing is moved further. Now it's a level flight. Then again it will transition here so that it can land vertically. Vertical descent. This is vertical takeoff, vertical descent. Right. This is tilt wing mechanism concept. Level hover, that is vertical takeoff, transition for level flight. After level flight, again transition for vertical descent. These are the references which have been used in this lecture. Thank you.